So when we're talking about bases, there's essentially two categories. You have strong bases, and those have hydroxide ions, or OH minus. And they're also commonly paired with a metal, making them an ionic compound. Then you have weak acids, and these really pertain only to the Bronsted, Lowry, and Lewis acid base theory. So they really just have a negative charge, and they're able to accept the hydrogen. But for this video, we're just going to look at the strong bases because they completely dissociate, which causes them to swap and drop. So when it comes to naming strong bases, they follow the same rules as ionic compounds because they are ionic compounds. So that means that you're going to name the metal or the cation first. Then you're going to name the hydroxide anion as is. And we name it as is because it's a polyatomic ion. Remember that just like in ionic compounds, subscripts don't impact the final name. So I don't want to say any di, tri, tetra. Let's name the following using the rules that we just listed previously. So in the first one, MgOH, the cation is magnesium metal. And so we just write magnesium, and then we're going to name the hydroxide ion. And that 2 subscript really doesn't matter. It doesn't affect the name, so the final name is magnesium hydroxide. Now in the second example, we have the copper metal or cation. Now, if you look, there's a 2 from the swap and drop. Copper is one of those transition metals, so we have to use the stock system, which means it could have been a 1 or a 2, but because we see the 2 by the hydroxide, we know that it's copper 2. And then we just name the anion as is, copper 2 hydroxide. What I would remind you is to make sure to use the stock system just like you would when it comes to ionic compounds. And another thing is, you look and see that the end of the name or the hydroxides repeat themselves always. So when it comes to writing the chemical formula, just like in other ionic compounds, you have to simply just swap and drop. And there really is no other rule other than that. The other thing that I would add, though, is kind of like a sub-rule, is that because OH is a polyatomic ion, remember, okay, that you should place it in brackets when the number that it receives, or the charge that it receives, is greater than 1. Okay, so just like you would with every other polyatomic ion, place it in brackets. Let's take a look at some examples. All right, so writing the chemical formula for the following, we have sodium hydroxide. When we look at the periodic table, we can see that sodium has a charge of +1, and hydroxide, of course, has a charge of -1. So when they swap and drop, and you get rid of the signs, you have NaOH. Now, when we look at the next one, now chromium in your periodic table could have a charge of +2 or +3. But here we can see that it used a stock system. And so we're going to use the 3 charge. So that means that chromium has a charge of 3+. Hydroxide has a charge of -1, just like in ionic compounds. You're going to swap those charges so that the chromium gets the -1 and the OH gets the +3. And then we're going to drop these as subscripts and remove the signs, which would leave us with CrOH. Now, remember, because it is a polyatomic ion, what we have to do is make sure to put it in brackets when the charge it receives is greater than 1. So any 2s or 3s, whether they're negative or not, it doesn't matter. So this over here is the final compound. And again, I can't stress enough, don't forget to put this in brackets. Lastly, calcium hydroxide. Calcium has a charge of 2+, and of course hydroxide has a charge of -1. When they swap and drop, your calcium gets the -1, your hydroxide +2. We're going to drop them and then remove the signs. And because your hydroxide is receiving something that is greater than 1, in this case a 2, we're going to put it in brackets and put the number outside the brackets. And so hopefully you can see that when you're writing the chemical formula for strong bases, it's really just a recycling of the rules for any other ionic compound. And that's because they are ionic compounds. They're just a specific type of ionic compounds.